Okay, this is Unit 7 Biomechanics in Sport Exercise Science, looking at assignment 7.3 Angular Motion. This is the final video in this assignment, and what we look at here is the kinetics associated with angular motion, the forces that are generated and the size of the forces that are generated to create angular motion, rotation around a given axis or fulcrum. So we know some part of this topic already. We know what a moment arm is. It's the distance between a fulcrum or an axis and either the load or the force. Okay, so we've talked already in the previous video about the load arm and the effort arm. Now we need to know that measurement. Remember, it's the perpendicular distance between the application of force or load and the fulcrum. In this example, you might see that moment arm, which is R, is 2 meters. What we also need to incorporate now is the force that is being applied to a moment arm. So this could be a force generated by the load being held or the muscular force being generated by the effort. Okay, let's keep it simple. So the components that we need to know to calculate what we call torque or turning effect or moment of force, all of those phrases mean the same thing. Your spec uses both of these, actually, turning effect and torque. Torque is the amount of force, angular force, generated. Now over here we've got the equation for torque, for turning effect. Torque is force in newtons times moment arm in meters. So I've already stated that the moment arm is clearly 2 meters between the fulcrum and the force. And this example gives us a force magnitude of 10 newtons. So the math is really simple. Torque is 10 newtons times 2 meters gives us a torque of 20 newton meters. Hopefully, fundamentally, you'll see that's a fairly simple calculation. So what's the torque? The force that causes angular motion, it's 20 newton meters. Here's some more examples to have a look at. So top example, we've got two moment arms. Okay, so there are two calculations for each of these examples. Let's do one at a time. So just looking at this top example, torque is force times moment arm. So the effort, green, moment arm, is 10 meters long and the force is 5 newtons. So the equation, if you remember, is force times moment arm, 5 newtons times 10 meters gives us a torque of 50 newton meters. So the effort gives us a torque of 50 newton meters. But we've also got to calculate the torque for the load arm. The load arm numbers, therefore, the moment arm is 5 meters and the force is also 5 newtons. So 5 meters times 5 newtons gives a torque of 25 newton meters. So the effort arm in this example is 50 newton meters and the load arm is 25 newton meters. This gives us sort of an effort arm which is greater than the load arm. Second example down here, the effort arm calculation. So the moment of the effort arm is 0.6 meters and the force is 6 newtons. So we're timesing 0.6 meters by 6 newtons and that gives us 3.6 newton meters. Similarly, the load arm is 12 meters and the force is 5. So the sum is 12 meters times 5 newtons gives us a load arm torque of 60 newton meters. So if you just work really methodically through each of the arms, the effort arm, the load arm, one at a time, then you can calculate the torque of each and compare. This up in the corner, obviously, typically speaking, in these examples, we would need to give a direction. Torque is a vector, it's got a magnitude, how much torque is there, but you also should relate to an example direction. So it could be that the load arm is going counterclockwise, i.e. downwards, and the effort arm is being applied upwards, so you're pulling up on this lever arm, which means there would be clockwise rotation because the effort arm is bigger than the load arm. So typically speaking, torque should have a direction allocated to it. Just to give you other examples, although they're not sports examples, it's an applied example just to help you understand the principle here. We've got an example of a sort of a wrench trying to undo this nut. We've got a short wrench and a force being applied. So the force being applied here, we've got a relatively short distance of that effort arm, which is 0.5. Now, 0.5 times an effort of 10 newtons, the force being applied, gives us a torque of 5 Newton meters. But we're struggling to undo that bolt. It's a really stiff, tough one. What we would try to do is we would try to increase that effort arm length because that gives us a mechanical advantage, comparatively speaking. So if we had a longer wrench, which had a distance of 0.8 meters, and we applied the same force to it, so we're not having to be stronger, we're just using a greater effort arm distance, that same calculation gives us a torque of 8 Newton meters. So with that additional torque, we can undo the bolt. Okay, so we sometimes manipulate these variables to give us greater torque. Of course, the other thing we could do is apply a greater force. We could apply a force of 15 newtons, and maybe that, that would give us a 15 times 0.5. That would give us a greater torque than 10.5, and we would be well away and hopefully be able to move the bolt too. So we can either manipulate, in this case, the length of the arm, make it longer or shorter, but we can also manipulate the force applied. Just a reminder, please don't use these examples in your work, please use sports examples. So just to summarize then, torque is a measure of the force applied to generate angular motion, twisting or rotational movement. It's called turning effect. It's the same thing. So we know that within the body, there's few opportunities to change the length of the load arm. So the main factor that we can change to change the torque is the muscular force. We can apply a lesser or a greater muscular force to manipulate the torque. We've got this weight bearing down. So we have a load arm with the force generated by the load, and we've got a muscular arm, an effort arm, and the force generated by a muscle. Now, obviously, in this example, it's a glass, but this could be a dumbbell. And if we want to lift the dumbbell up, we've got to have a greater torque in the clockwise direction than we have being applied in the counterclockwise or anti-clockwise direction. So remember that torque is a vector. It's got a magnitude, how much torque is there, and there's a direction. So we should really refer to up, down, clockwise or counterclockwise. So torque is affected by a few things. Obviously, how much force is applied, the direction it's applied in. If it's perpendicular to the object or at an angle, that can affect how much torque there is. It's more effective if it's perpendicular, so at right angles to any given load, and the location of the force application. So within our body, we can't change this significantly. Outside of our body, sometimes we can change where the load is applied, the distance from the fulcrum. Okay, this next concept really, again, is a little bit more icing, quite tough to perhaps understand, but realistic to why phases of exercise can feel more challenging than others, even as simple as doing a bicep curl. If you can recognize that the effort arm in the different phases of the bicep curl, it changes the perpendicular distance. So the effort arm actually at the start is only 3 centimeters. So we know that if the effort arm is quite short, it's harder for our muscles to generate force. when it's in the sort of 90-degree phase, the distance between, the perpendicular distance between the fulcrum and the effort arm is 4 centimetres, so it's bigger. Remember, it's not the distance to the attachment, it's the right angle distance, the perpendicular distance. So it goes 3 centimetres at the start, 4 centimetres in the mid-range, and then as you get to the top range of the bicep curl, it reduces again because the arm is angled, the attachment, the perpendicular distance is less again. So 3 centimetres. So our effort arm is actually less effective here, more effective here, and less effective here, or less advantaged here. So if we assume that the force generated by the biceps brachii is 10 newtons, and we can now calculate torque for those two positions within this same action. Where the effort arm is slightly longer, we would get a calculation of 10 newtons of force times by 0.04, gives us a 0.4 Newton meter torque. So we generate greater force in that mid-range when we're looking at this internal lever system. However, at this slightly higher, or even would be the same for this lower one, this different angle, where the perpendicular distance between the fulcrum and the application of effort is 0.03, we have 10 times 0.03, we have 0.3 Newton meters of torque. So the first and last position are less mechanically advantaged than this middle phase in terms of this internal lever system. So what we can observe here is that based on purely the internal lever system, the effectiveness of the torque of the biceps brachii varies depending on the position because that perpendicular distance from the insertion varies, goes from 3 to 4 to 3. Now, unfortunately, what we have to deal with is also the load arm. That was purely talking about the effort arm. We talked about the distance between the fulcrum and the attachment of the muscle, the effort arm. But within this same exercise, we have to look at the variations in position within that action of the effort arm. So let's have a look. This is the perpendicular distance between the application of the load, the gravity acting down through the mass of the load, and the fulcrum. So this distance here. What we can see is that in this first position, we've got quite a short load arm moment distance. In the middle phase, it's longest, which means it's more challenging. There's a greater torque acting on it. Just moving outside or moving beyond that 90 degrees, we've got a moderate load arm moment, and then going up to the top, A and D are the same again. So unfortunately, whilst the muscular torque was better in the middle, what we've got in that 90 degrees middle phase is the greatest load arm torque also. So they don't completely cancel each other out, but they are, opposing against each other, if you like. We've got the greatest challenge based on the load arm in the middle, but we've got the greatest strength, relative mechanical advantage for the muscle, the effort arm in the middle also. We can see this in other examples, how we manipulate our body position to increase or decrease challenge by changing the length of the load arm. So a straight leg raise has a very long load arm. The weight of your feet and the legs all extended away from the fulcrum gives a greater load arm. Harder work for your hip flexors to do a leg raise. However, if ignore the fact that they've got a weight in their feet, if they just did a bent knee leg raise, then that would be easier. The load arm is shorter, less counterclockwise torque. If they add a weight, of course, they're adding a force, a downward force, they're adding counterclockwise torque. So we manipulate what we do a lot of the time. So please remember that throughout all of these sections, you need to give a variety of sports examples to show your understanding, but you must give some gymnastics examples throughout also. So that's the end of the lever section. We've looked at in the previous videos the functions and types of levers, and this video focused on torque or the turning effects how we do calculations to generate the size of torque based on the moment arm length and the force applied.